All right, we'll pick up where we left off, but first let's talk about homework. I had a lot of interesting questions in office hours. I want to open it up right now. Who else has questions about the homework due tonight? All right, I'll go over a couple of, oh yes.
Instead of if our model is like more it's like regression based, would you be content if like these were errors opposed to accuracy, or do you want us to?
That was one of the questions I got. This is a very good question. Let's talk about it. So if you're doing regression, let's say you're trying to predict the price of a house. There's more than one way to handle this, and they're both right, okay? So you have some neural network that takes in some features and it's going to give some number. Let's say, you know, a house price. We've got to judge the goodness of our model. You don't want to say just accuracy, right? Because let's say that the real house price is $300,000 and your model outputs $300,001. Is it accurate? Well, it's not exactly right, but you want to let the model feel good about that, right? So we don't want to punish that. So one way to handle this is to say, I'm going to call it right whenever it's, you know, within some bracket above or below of, you know, 20K. And then whenever it's in that, we'll call it accurate. Whenever it's out of that, it's not accurate. Then you can get an accuracy number. You can get most of what else you might need. Accuracy applies. Confusion matrix doesn't really apply. Try to understand what the metrics are for and use whichever metric works best. Now, another way to judge this is correlation. Like, let's say you have 3 input vectors, and the real values are, you know, 300K, 250K, and 900K. Your model predicts 307K, 2200, very small, and 10 million. So maybe it goes up where it should go up, and you know it's medium where it kind of should be medium. It goes down where it should go down, but it goes down too much or it goes up too much. Well, one way to judge how closely your thing really tracks, your predictions track with this, is called the Pearson correlation coefficient or score. And PyTorch has this, Python has this, there's a bunch of implementations out there. Just use whatever someone else has done. And all you got to do is, it's just like when you compute your loss. When you compute a loss, you give it your actual Y and you give it the predictions, right? And then it comes back to you with one number that tells you on average how lossy you are, how average you are, how bad you are, or your error. Pearson correlation coefficient gives you one number that tells you how correlated these are. So again, if you're using regression, this is one way to go. This is another way to go. You can do both. Whatever you do, motivate it. Talk about in your comments why you chose this or that. You look at, you might have a question.
Yeah, for the correlation, if it's, what do you mean by the number? Like it's like between 0 and 1?
I think it is.
Okay.
And it's a well accepted number in statistics.
Okay.
Pearson correlation coefficient or score. And I think that was the most important thing that came up in the office hours too. I will go through a little more stuff in a little bit that might help. Okay. Now, this stuff with making fake faces, very soon we're going to be making fake video. I saw a demo yesterday of someone who had, some video of a real person, a woman, a news reporter, and she was just talking. I don't remember what she was saying. And then they had the computer generated version of her right next to her. I could tell it wasn't her, but if I hadn't seen the real one, I might think it was real. Generated video is, yes.
How is this different? Like there are already videos out there that exist that have been edited. Like saving computers that do happen. So how is this different?
Okay, yeah, so this is very different from face swapping. Remember face swapping? Or,
I mean like videos of people talking. I'm thinking of like particularly like people editing.
Yeah. What year was it? It matters. Depending.
Probably 2016.
Oh, okay, a long time ago. If it was a long time ago, the first one they did was actually Jordan P. from Key and Peele. Remember him? He can imitate Barack Obama's voice perfectly. So what they did face swap. Face swap basically takes a high definition real image of a real person, and you use neural networks to understand the way the muscles move. So you first of all take a normal person and you get a map of their face. You select certain specific points. This is an early version, but real versions now, there may be 200 or 300 points on the face that system will automatically see and know where they are. Now, in the old days, when they would do face transfer, they would do it with things like in the Lord of the Rings. That was more than a decade ago, right? 20 years ago, right? The Lord of the Rings, they had Gollum, this character, acted by someone Andy Serkis, who wasn't even in the movie. He was just, his motions ended up in the movie. And the way they did is they had his body covered with these little white spheres and had some on his face too, or dots drawn, so that they could look at that and a computer would map every point on his face to one of these points. Then, as long as they took high definition images of him, video of him, they could use a computer to transfer that into the virtual world where their animated character in photorealism was being generated. That was more a mathematical thing than generative. There's no generation of an image. And this kind of thing was also used with the Jordan Peele Obama thing. They would figure out the points in his face, and they figured out the points in Obama's face. But what was different about that was they used a neural network to learn how you contort a face when it says certain syllables and sounds. When you say a P, a B, a G, duh, what does that look like? And they just mapped that. And the audio was not generated, it was literally his voice. But what's coming up in the future is the ability to make it from scratch. You're not using a high definition image of a person and contorting it, you're just generating it from scratch. And maybe, you start off with, President Obama and have it generate something that's halfway between Obama and Bush. You can even make it look halfway between them and sound halfway between them and have mannerisms that are halfway between them. I mean, there's a lot of weird possible stuff in the future. Yes. It could, and it could, but I hope it doesn't. I hope that we dig deep inside our human selves and come up with something poetic to express that here's consciousness. That could come out in a voice, the way you talk, the way you do things. I suspect that in the future we will all become very attuned to whether or not it's artificial character. I mean, the newest Star Wars movie had a couple of dead actors and actresses in it, playing their parts again, reprising their parts, and they were their young version. It was generated from scratch. Also, Paul Walker, when he died, he was still in the end of the last, or one of those Fast and Furious movies, even though he'd already died. They had his brother, stand in, and they generated the computer character over him. When I saw it the first time, I was like, oh, it's pretty real. I mean, I knew the character was dead, but I was like, oh, it's pretty real. But with every passing year, a couple of years, you go back and look, and it's not as real anymore. You're going to get better and better at noticing these, and you may even notice it with voice acting. You may long for the imperfections of a human voice. We'll see. Okay, so there's going to be lots of ways to trick you. And one of the ways people are going to try to trick you is to get your money. And you'll come across things like this. What's wrong with this situation? What does the tagline say at the bottom?
I can't see the bottom, but I was gonna see chairs over there, like they're literally cut off at the bottom, right? Like,
Yep.
those don't look like actual stairs.
That might be an issue too, but that's not really, the real problem is that blondes do it better, and this person is obviously not blonde. So this is a bot generated this to try to trick somebody. Here's another one, and this one actually happened to me. This is someone I know. And this person lives in Winterport. I asked them, where are you? They said, oh, I'm in Winterport. I knew this person, I knew they lived in Winterport. They contacted me on Facebook, but this is totally fake. Her account had been hacked. And I even looked up this thing, the American Hope Resources, whatever. I looked it up, and it's a scam thing. So people will come to you and often talk to you in a voice or a manner, at least in text, that you recognize. But what if they even came to you, called you on the phone? What if a number that had been spoofed called you on the phone and they were pretending to be that person and they even generated their voice? That is scary stuff. There's also something called timbre modeling. Okay, this you guys should totally watch sometime. This woman, I don't know if we can even get audio, we'll try. This woman created a model to make anyone able to sing, not just talk, sing in her voice. Yeah, there's no audio, so please look this up and watch this when you get home or sometime. What if you could sing in your favorite musician's voice? And she's made it open source, so anybody can literally download this and sing in her voice.
You could try turning the ear volume up, but I don't know if that really picks down the,
This,
right.
this, yeah. Let me show you the best part.
This way, but yes, the truth is, show you every day.
You love to stay.
So it's pretty amazing all the ways the world is going to be able to entertain us and trick us. So you guys got to be more careful every year you're alive. And it's all because of neural networks. So again, going back to the model of a thermostat, remember, you have some input. You're going to, have, let's start here. The output is a real temperature, right? And you have some desired temperature you want it to be. The error is your loss. Maybe you want a temperature to be higher. Maybe you want it to be lower. That's your loss. And you really only have one neuron. You're going to make things colder or hotter. And then you test the output again, and you keep doing it, keep doing it. So those three things, or four things: input, loss, optimizer, output. This is the basic training function. So you have some batch of data. Now, it could be all your data, but oftentimes all your data doesn't fit on a GPU. The other thing about it is if you choose a small batch of data, not only does it fit better on a GPU, but maybe it helps you get going in a direction. And if you have all the data at once, oftentimes, mathematically speaking, it's hard to choose a direction because every sample is going to contribute a different set of gradient vectors. Okay, so we have this batch. Y is the output, X is the input. For epoch, you range number of epochs. One question I had earlier was, what's an epoch? So I'm going to ask you guys, what is an epoch? Yeah, one run through of all your training data. And if you have enough training data, you only need one epoch. GPT-3 was trained with one epoch. It was 1.1 million years of English if you average 20,000 words a day. And they just one run through. But usually I would do maybe 1,000 epochs, depending how much data I have. For batch and get batches. So that thing at the top, actually ignore that because I do it twice. Forget that. This is the one that matters. For batch and get batches. So you're getting one batch to chunk your data. Now I like to use 50 as a good rule of thumb for my batch size. And it's not just for GPU memory. It's because of the work of a guy named Mike Murphy at Berkeley, talking about how of all the hyperparameters that you might change in order to train a neural network, and again, hyperparameters are things like learning rates, the values that go into your nonlinears, the nonlinear activations, the length of vectors, the width of each layer, all these are hyperparameters. Out of all the hyperparameters, the first one that you should try to experiment with and tweak is batch size. That's what Mike Murphy's research, also involving something called random matrix theory. And he basically said a rule of thumb is about 48 or 50 or so. But you can try more or less. So let's say you have a batch. Now, this model object, it looks like it's being called as a function there. Why is that? Why are we calling this model object as if it's a function? And if you're the one I explained it to in office hours, feel free to speak up. All right, so when you create a model in PyTorch, first of all, you want to subclass the typical PyTorch model. Whatever you do, I really suggest you follow a tutorial or some of the code online. There's only 1 million examples. So when you create a model, you want to create some class model, and you want it to be a subclass of modular. When you subclass this thing, you guys have all taken object-oriented and know subclassing, right? Okay, so when you subclass this, you get a bunch of things for free. And one of the things you get for free is that in here, I'm going to have a forward function, right? This is what the forward. This is the steps that a neural network will take when you run it forward. And self just means, it's a method of this object. X is a list or a tensor with more than one input vector in it. So it's always expecting that to be a vector inside of, a tensor. So one example is, let's say you have a 3-dimensional input vector. I hope yours are longer, but if it's just 3, then I can only do 3, 4, 5, 6. So we have input length of 3 for the vectors. What is the batch size? Yes, because there's 3 of them. So your batch size is also 3. X here is expecting something of this format. So if you want to throw in just one vector, that's fine. Make sure it's inside of the matrix. It just happens to have one vector in it. Okay. Sometimes people list them vertically. Make sure you do what your thing expects. Okay. One of the things you get for free is shorthand, like a shortcut. If you want to write, let's say you instantiate this model somewhere else in your code, you say, model equals model, and you've made it. Okay, this is the instantiation of that model. Now we're in the training function up here, and I need to run the data for a batch forward through the model. Okay, so there's this nice thing where I'm writing too small. Sorry. I can, if I want, I can do that if I want to, or I can just do this. That's the same thing. So pretending your model object is a function, this gives you that shortcut for free. So you just call it and it runs the forward function. Okay, so when we go forward, we get our output, the predictions of the model, the output of the model. It can be right, it can be wrong, who knows, we're about to find out. So we have some loss function. It could be the L1 norm. It could be the L2 norm. It could be cross entropy. It could be any other loss function you can find out there on the internet and want to use. Some people have custom ones, some people make them up. Now, a lot of the loss functions are written in a slightly uncomfortable way so that they will be very efficient on a GPU. There'll be some criterion object and you can preload that onto the GPU. But you might want to just write it in the line. Like one way is if you have a bunch of Y values and you have a bunch of predictions, you got to compare them somehow. And if your batch size is 3, then you've got 3 Ys and 3 predictions. They're just vectors, right? So you could just subtract one from the other. And you would have to, you'd want to take the absolute value of that. And this, if you do it right, I don't remember if the ABS or a NumPy version of that, but what you want to end up with is a vector, which is the difference between them, right? The difference. But it's a vector. It's going to have different values. Like you might have, if the first prediction was off by 1, you'll have a 1. If the second prediction was 2 below, maybe it will be a -2, but since you took the absolute value of the 2, maybe the next one is 0. You got the next one right. Yay. Well, we need to have one number that represents this. What should I do? Come on, guys. You by the way know. What should I do? Average. That's good. That's a perfect way to do it. So NP mean is good. So NumPy mean function is a great way to do that. Some people just, add it up, but then your loss is going to be bigger if you have bigger batches. So that maybe is not great. Average is the way to go. You could also do, by the way, actually, I'll ask you in a second. What kind of loss is that? Square root of what?
Wait, some. Oh, okay. Thinking about that. The squared sum.
Yes. What were you going to say?
I was.
Is that what you're going to say? All right. So what?
Should be at 2.5.
Oh, yeah. Good point. Thank you. I love getting corrected, by the way. So one of these, the first one and the second one of them is the L1 norm, one's the L2 norm, which is which? Yep, this is the L2 norm. And L2 norm is also called mean squared error. And actually, that's what PyTorch calls it. They have something called mean square error loss. L1, they call mean absolute error. And absolute comes from that absolute value function under that. Use either one of these or anything else you want to find. Okay, so now we've only gotten this far. That's a lot of talking for 3 lines of code. Okay, this backward function is very special. Now, when I think of taking the loss, I think of I'm getting a number, right? Just a number. How can a number have a backward function? Does anyone have an idea? If you're one of the people I explained it to in office hours, feel free to speak up. Okay. So this loss thing in PyTorch and TensorFlow both, it's going to be an object actually. It's not just a number. You will have the number in it, and in PyTorch, that will give you the number. If you want just the number, like how far off you were in that batch, that will give you that. But this loss object has so much more. It has pointers back through your network. So this lost object starts here. And it knows about the two neurons that may have, led into it. And that loss object lets the backprop algorithm go to here. And then from there, it knows what to do to go here. From there, it knows what to do to go here or to go there. That's all contained just in here. It makes things so much easier. In the old days, when you were writing this yourself, you had to write code for a bunch of neurons and then know where you were, make sure you got everyone correctly. And this just recursively handles it for you. You guys just got to be so grateful that you're living in easy times. So you just call backward. It's so easy. And remember that you end up with a gradient. Now, what exactly is that gradient? Well, let's pretend you have, 2 input neurons, 2 middle hidden neurons, and 1 output neuron. Okay, so you get some error at the end. And we figured out based on that, okay, we're going to make the bias in this neuron a little higher. And the weight from here to here, we're going to make that a little lower, let's say. Just that's how the weight, that's how it came out. And this one a little higher. And then the bias in this neuron a little lower. The bias here a little higher. And then this goes up a little bit. This goes down a little bit. This one happens to go up a lot. This one goes down tiny bit. So these inputs don't have biases. Your input vector, if it's a length 2, it literally goes in here and here. And that's the number that goes down this line and down this line. And there's a number hidden in the line, the weight of that line. It will be multiplied by the literal number that was here. And then added, you add the bias of this neuron right here. But you only add it once, not for every link. So now, this lost backward thing, it brought the gradient through. It figured out which part of that had to go here, had to go here, and had to go here. And if you ever want to do a deep dive on the actual math, remember it looks like this. It's the chain rule again and again, approximately. So even though we brought these back here, we still haven't applied that gradient. We haven't changed the weights and biases yet. We just told them this is how you should change. Now, the problem with applying the gradient immediately is that gradients are usually big, too big. So we have some function like this. So let's say it's not convex. And we're here. The gradient says, I would say, no, would be here. The gradient says you need to go this way. Yeah, let's do that. Gradient says you can go this way. And if we go a lot, we end up, over here. And we could just keep going back and forth. That'd be a bad thing. Another situation is if we are here and we go a lot, maybe it works the first time and we end up here. Then we go a lot the next time and we end up here. Then we go a lot the next time because it's still kind of the same angle and we end up over here. And you just keep going back and forth, bang, 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 and you never settle down. Or maybe you end up banging around here. What you want is you want to go just a short distance. So we take each one of these numbers and multiply by the learning rate. And a good learning rate to start off with is usually 0.001. So you're going to take this weight and make it higher, 1,000th of this value, 1,000th of this value, 1,000th of this value, 1,000th of this value. So you make a tiny adjustment, and it works better. Sometimes I do start off with a slightly higher learning rate, but eventually, let's say you're up here and you go down here with a big learning rate, down here with still big learning rate. Once you go for a little while, you want to make it smaller and smaller, 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 smaller. And it'll never be perfectly accurate, but you might find one of these nice, relatively low places where it converges. Converges means, it's going to be going towards some local minimum, and it's not going to get better after that. But maybe it's good enough. In a lot of high dimensional models, rule of thumb thinking leads us to believe, not that anyone can visualize this really, but leads us to believe that there are often many, many local minima that are just as good as each other. So if you were to retrain GPT-3 all over again with another path to that same data, because of random settings, it would come out different, but it'd probably be just as good. Okay. Lost backward brings the arrows to everywhere they have to go. Optimizer step applies that change to the feature with the learning rate. So if you don't do optimizer step, you're not actually changing your network. And SGD, stochastic gradient descent, is one popular optimizer. Atom is another one. Atom is supposedly a little better. There's a bunch of others. Use whatever you want, whatever works for you. If one doesn't work, try another one. This is just housekeeping. I think it's sad they still make us do this. It should be done automatically. Come on, just zeros out all of these arrows. So when you do it again next time, you won't get residue from last pass. Is there any step in this training loop that you want to ask a question about?
Can you spell lost cell backward again?
Mm-hmm. Yeah, sure. So when you run your data, a whole batch of data, like let's say 3 vectors that are each length 3, or 2 in this case, those vectors come in here, they go to here, you end up with, if you have a batch of 3, you end up with 3 errors. And it could be, one's a little high, one's a little low, one's a little high, but it averages out to this. It's just one number now. And we're going to say, what can we do to change this network such that this final number boosted up a little? And the loss object contains everything PyTorch needs to know, or TensorFlow needs to know, do this for you with just one function call backward, which is beautiful. That it just outputs that your loss function. Because of these are tensors, this prediction tensor specifically. The prediction tensor came out of here. And it wasn't just a number either. You can print it, look at the number. The number actually be the default thing it renders on the screen if you print it, but that tensor knows where it came from. So just giving it some values that did not go through your network and some values that did go through your network PyTorch will get enough information in this loss object such that it can do that math we saw. The derivative of this error with respect to this weight. The derivative of that with respect to this. The derivative of that with respect to this and this. And then the same thing here. And when it applies all those chain rules, just this one step, loss backward, will put the right arrow at the right parameter. Now, we have talked about a gradient, which is a direction to go in high dimensional space. So if you have like a, let's see, if you have a 9-dimensional hill you got to climb, or hill you want to go down, let's say this is, a 9-dimensional space. There's all kinds of other dimensions and everything in here. Every point in this space represents, it's a coordinate with 9 dimensions, right? Those coordinates are the parameter settings. So maybe coordinate 1 is this weight, coordinate 2 is this weight, coordinate 3 is this weight, coordinate 4 is this weight, and so on. And this bias is coordinate, this bias, and this bias, and this weight, and this weight. Those are your 9 coordinates in this 9-dimensional space. And you're trying to figure out what's the direction I should go in 9-dimensional space. And what's very nice is almost immediately out of that math comes, well, it's a vector, right? So it's going to have components. You're going to have, the Z component, the X component, maybe there's, a Y component, and there's going to be 9 components because it's a 9-dimensional vector. Those 9 components are these 9 arrows. So you figured out these are actually 2 ways of thinking about the same thing. The actual math behind the scenes is very straightforward and ugly looking, but it's basically doing this. But remember, you don't want to go down too quickly. You want to apply that 1,000th of a step or 10,000th. And as you go through your epochs, you want to make it small. Some people make every epoch be like 0.95 the learning rate of the last epoch, or 0.9 or something. So that all happens when the arrows get applied, the loss backward, then the optimizer step actually changes the values. Does that answer your question, Claire? Okay. All right. So if we have that first model, or this is one model with 2 layers, okay? Each one of them is called a dense layer. Oh no, these are 2 models, 2 separate models. So model L1 and model 1 and model 2. If you use the summary function, just prints out, some basic aspects of the model. Dense just means that every neuron is connected to every neuron. We only have 1 layer in the first one. We have total params 24. I don't see inputs. There's something missing here. I'm sorry about that. Let's just look at an example on the board. First of all, before I erase it, how many parameters? I said it several times. Nope. 9. Because every bias and every weight is a parameter. If I have a neural network, like I'll just draw a layer like this. 1, 2, 3, or 4 layers. Let's say there's 3, 3, 2, 1. How many parameters will that have? I want you guys to think about it for a minute, and then we'll do some guessing. Okay, we're gonna ask you all to write down a guess. Write down and type it or something. Want to record it for your own personal enjoyment. Okay, let's break this apart. This layer has 3 neurons, and it's outputting to a layer with 3 neurons. So there's going to be 9 weights. There's 3 neurons here, so there's 3 biases. 3 neurons going to 2, there's going to be 6 weights. And of course, 2 biases. 2 to 1, going to be 2 weights and 1 bias at the end. So all in all, 9 plus 3 plus 6. Someone please add this up for me. 2 plus 2 plus 1. Did you say 32?
No, wait. 23.
23. All right. So 23. Who was exactly 23? Who was higher than 23? Raise your hand. Who was lower than 23? All right. But you guys are getting the gist, right? And you can always get the parameters by doing dot parameters, opening close parentheses, I think, on your model. Okay. Now, the last 5 minutes, we'll dive into one deep topic. Okay. Every neuron, it's got things coming in it and one signal coming out that then goes multiple places. But it's a function in and of itself. Think of it as this one neuron is a linear model of everything that came into it, right? It's just a linear model. You look like you're not green.
Are those these squares on the left as other neurons?
Yeah, imagine it's signals coming from other neurons in the previous layer. But this one neuron, it's just a linear model of the signals that go into it. Now, after on its way out, it goes through a nonlinear activation function. And that part is nonlinear. But this, when it goes on right here, it's just numbers being multiplied by numbers and adding a number. It's a linear model in this one tiny scope here. So neural networks in the larger case are just whole bunches of linear models. And we had a lot of hope before we understood them better. We had a lot of hope that they were doing kind of semi-magical, high-dimensional mapping from one space to another, and that there's all this beautiful math occurring in there. Turns out to be a lot more mundane, sadly. Now, the picture gets muddy, it gets blurry if you use tan H's or sigmoids for your activation functions. Not that those are bad, but there's nothing particularly magical going on in the edges of those functions. So it turns out there's not really a great case to use them. Let's consider the case where we're using a simple ReLU. And remember, a ReLU looks like this. Meaning, remember, every neuron is giving one value out. And if that value is below 0, well, then the actual value that goes out to the world, to the next layer, is 0. Anything below 0 gets just zeroed out. If it's above 0, then it's a linear function of that 1, 0. Overall, the whole thing is nonlinear because of this one change point. So we call it a nonlinear activation, but it's the simplest of the nonlinear activations. So if we're using this, then what we can do is for any given input vector, let's say we have some input vector, of course, every input neuron will have something in it, right? We apply this after every neuron. Some of them will be 0, and we leave those as gray. Some of them will have a non-zero value, and we'll make those green. So for every input sample, we'll probably have a different pattern, right? Now in computers, we talk a lot about addressing things, giving things an address. Everything in memory has an address. Like you create some object and you ask your computer in Python, I forget what the function is, but you can ask it, what is the memory location? What is the memory address? Well, we're gonna theorize a different address system now. Let's just have it to be a binary address system. Remember, you have all those parameters? Well, we're going to make, instead of dealing with all the parameters, let's throw out the weights. Let's just deal with the neurons themselves. So if we have 1, 2, 3, 4, 5, 6, 7, like 15, whatever, 16, whatever it is, neurons, we're going to have one element in our address for every neuron, and it's going to be a 1 or a 0. So maybe the first 3 look like they're all 1s, and then 0, 1, 1, 0, yada yada yada, all the way to the end. So every individual input vector can be given one of these. You guys follow me that far? This is our theoretical address. If this were the world, we wanted to have a postal service, this would be the address you write down to get to some theoretical location. And it corresponds to this. Now, why is this important? Well, it turns out that now we know neural networks, we're not doing something beautiful and wonderful in curvy high dimensions with our data. Really, this corresponds to a polyhedron, some faceted high dimensional geometric object. It's not square or a cube, it's not regular, it has random edges, but all the sides are flat. And if you want to visualize it, this is not what it would look like, but hey, it's a good place to maybe start. Imagine each one of those sections of volume is having a random shape, but instead of in 3 dimensions, we're talking about parameter space, many more dimensions. But we can split that parameter space into these polyhedra addressed by this system. Then you could go into one of these polyhedra. Just let's go inside this one and move around this space and see for different coordinates within that little polyhedron, how does our output change? Turns out inside there, it's pretty much a linear model. So even though neural networks are beautiful, so useful and wonderful and cool, and they have all this great functionality that we're using and discovering and improving every day, at its core, it's just a library of linear models. And for every individual sample, it pulls a different one off the shelf. This is not exact. This is a simplification, but this is a closer simplification than what we used to tell students. Literally what I told students last year. And this changed because of this guy and this guy. So this guy, Balestriero, came with a paper that said what I just told you, but it was called the spline theory of neural networks. That's one to look up. And this guy says that everything is extrapolation. We used to think that neural networks interpolated in this cool, smooth space fields, but no, everything's extrapolations. Everything is wild guessing almost. All right, thank you guys. See you next time.